Hi everyone. Today I'm going to talk to you about some work we're doing in the tallest mangrove forest on Earth, looking at pretty extensive sensor intercomparison and biomass estimates. So we have so many ways to map mangrove biomass, but which do we choose and why do we actually choose them? This is the purpose of the Gabon AFRISAR campaign that basically enables us to do these massive sensor intercomparisons that are relevant to airborne and spaceborne missions aimed at measuring forest structure. So for this work, we compared a pretty extensive range of different types of sensor technology. We have stereooptical with the ALOS DEM. We have the C-band radar with the SRTM mission, L-band radar with the UAVSAR, waveform LiDAR with ELVIS, which is analogous to the JEDI mission, and tandem X data, which is X-band radar. Resolutions ranging from 12 meters to 90 meters. Now, this particular field site, Pangara National Park, has short stature stands and massive stands that reach around 60 meters in height. This is the tallest known mangrove forest on Earth. So what we're doing here is we're basically taking an array of field plots, 18 in total, match them up with our remote sensing data and with the inventory data estimate biomass that we then use to create a calibration for wall-to-wall biomass estimates, and then we're going to compare all the different estimates from all these 5 different sensors. Here we can get an idea of the distribution of heights in this mangrove forest, where on the west side we have low stature or short stature forests, and then on the east side have the 60-meter tall stand. So what do we see in terms of results? We found around 2 teragrams of variation in the total biomass estimated purely due to different sensors being chosen in this area. So why is this? We can drill down and start looking at the biomass density distribution depending on sensor. So if we look at tandem X, we notice that the 12-meter highest resolution tandem X data ends up being more sensitive in the low stature stands, as well as more sensitive to the high biomass and the tall stature stands. As we coarsen that resolution to 90 meters, we end up reducing sensitivity in the extremes. Now, an extreme example of this reduced sensitivity is with this passive optical stereo DEM from ALOS, where we end up having significantly reduced sensitivity in the low stature and the high stature stands, with most of our biomass density occurring around 190 megagrams per hectare. With the global SRTM data, we end up seeing a saturation in the high biomass range that we end up being able to actually fix when we fit a local model to the SRTM data. With UAVSAR, we have reduced sensitivity in the low stature stands, and then we see a similar result with the ELVIS data, which is relatively comparable to JEDI. Now, this work is part of a much more extensive sensor intercomparison where we're comparing around 16 different biomass estimates, as well as some other more coarse resolution global estimates. In terms of some interesting results we see from this upcoming paper, we looked at the disagreement across sensors with canopy height and found an increasing disagreement with increasing canopy height. And in terms of relative errors, we're seeing the highest disagreement in the lowest stature stands, which is going to be of pretty substantial importance because the majority of mangrove stands globally are this medium to low stature. So I'll say thank you for your time.